Hello, everyone, and welcome to today's webinar presentation, The Secret to Unlocking GraphQL at Scale, presented by Apollo. I will turn it over to Lenny Burdette, Principal Solutions Architect at Apollo. Lenny, please take it away.
Hello, everybody. Thanks for coming to this talk on the secret to unlocking GraphQL at scale, lessons from 4 years of federated GraphQL. My name is Lenny Burdette, and I'm a principal solutions architect at Apollo Graph. One of the coolest things about my job is that I get to work with a ton of amazing companies across so many industries, building some of the most sophisticated, largest, highest throughput GraphQL APIs in the world. So if that interests you, check out our careers page at apollographql.com. We have openings all over the place, including the solutions architecture team with me. Today, I want to start out with a really brief introduction to GraphQL, just to set the stage for the rest of the talk. And then I'm going to do an introduction into Federation, our solution for building GraphQL APIs at scale, talking about why we built it and generally how it works. And I'm going to spend the majority of the time on how we designed Federation 2, the new version of Federation that we announced in April of 2022. All the lessons we took from working with customers on the pain points and the improvements that we can make to this incredible technology. I don't want to spend a ton of time on GraphQL, especially because there's a bunch of great resources out there in the wild, including our own tutorial series. You can start with the liftoff tutorial here, which is a self-directed course, and you work your way from scratch, knowing nothing about GraphQL, all the way up to building a GraphQL API, running it in production on the Apollo platform. But just as an introduction, GraphQL is both a query language for clients and an execution engine for servers that Facebook created in 2012 and open sourced. And it's an amazing way for clients and servers to talk to each other in a declarative, type safe, and comprehensive way. To show you what I mean, on the left here, I have the schema for a GraphQL server. This is a way that the server declares all the capabilities that it can provide to any client. Capabilities like fetching a product by ID, fetching the name and ID of a product, and even traversing the relationships between that product and other types like the review. On the right, I have a client operation. This is how a client indicates the requirements it has of the API in order to render a view or build some other kind of experience. And this particular operation, we're exercising the capabilities of fetching products and some basic details and traversing that relationship. There are two things I'd like to point out about both of these examples. Number one, both the schema definition language and the query language are declarative. They describe what we want to have happen, not how to do it. It's your code that will actually execute these capabilities and provide data. But the GraphQL query language and schema definition language is declarative and allows us to build some really amazing tooling on top of, including federation. The second thing I like to point out is that the client operation selects only the requirements that it needs. There are more things in the API than what it's fetching. And this field selection property of GraphQL has some really great benefits. The most obvious one that a lot of people flock to GraphQL for is the fact that you're probably going to be sending less data between the client and the server, which is really great for bandwidth sensitive applications like mobile apps. The client is only going to get the fields that it asks for and nothing more. But this is also a really amazing way to deal with really large APIs and lots of diverse clients. You can build your GraphQL schema so that it's entirely comprehensive. That product type could have hundreds of fields, but a client can then specify only the fields that it needs for that particular user experience or view. This means that you can support all sorts of clients with one API. And the client really gets control over what the API shape is, while it delegating all the responsibility for executing these capabilities to the server. On the left here, I have an example of how you can make a GraphQL request. This is a little JavaScript snippet that fetches that exact operation over HTTP and gets the response back in JSON, which is what's on the right. The JSON response maps really closely to the GraphQL request. Everything's ordered in the same structure and usually aligns really closely to like UI components in your React application or your Swift UI application. One thing I'd like to point out here is that we're fetching all the capabilities from one single endpoint. Typically, it's called slash GraphQL on your API server. And there's some really cool properties to this, especially from a business value standpoint. You're going to get a lot of consistency across your clients, whether they're mobile apps, web apps, Internet of Things devices. They're all going to one place to get all the data and all the relationships across your entire API. And this means that you're going to get a lot of consistency as your customers move from touch point to touch point. It generally means that you're also going to have a lot less redundant logic in those clients. Again, because you're delegating the responsibility of executing these capabilities to servers, the clients end up with a little less code, especially for doing things like traversing relationships in your data model. This ends up being a great way to address the shortcomings of architectures like backends for frontends. A lot of our customers started with backends for frontends, building client-specific APIs, and realizing that they end up being very costly because you're repeating a lot of logic and functionality across all these endpoints, and it's hard to keep everything consistent when you're shipping so many services at once. So you end up with an API or an architecture that looks like this. All of your clients talk to a single API and get all the data in your API and all the capabilities come from this one place. There are lots of benefits to this, but there are some drawbacks, especially for organizations that use a microservice architecture. And this is one of the things that drew us to invent what we call federation. I'm not really going to get into the whole microservice versus monolith debate today, but there are definitely some valid reasons for choosing microservices. Some of them include the ability to uh, support multiple languages and platforms, having different some services be in PHP and some services be in .NET. The fact that you can have teams distributed across the globe in very different time zones, and they can operate independently by owning their own services. And the fact that if you have hundreds or thousands of engineers contributing all to the same set of services, it can be really hard to coordinate all those deploys and then deal with rollbacks if one team were to introduce a bug and it affects everybody else. But how do we resolve the tension between microservices, where work is distributed across many, many machines, and GraphQL, where you're providing all the capabilities from that one single endpoint? When addressing this problem, we went to a classic architecture in the microservice canon, the API gateway architecture. This means that one of your services sits in between the complex world of microservices in your organization and the clients on the other side, acting as a facade, abstracting away all that complexity. And a lot of uh, companies adopt GraphQL in this gateway, writing a bunch of code to execute all those capabilities, making requests to all the microservices to fulfill a single GraphQL request. This works for a while, but it does get really hard to scale. It ends up being a monolith in the middle of all your microservices. So we thought, is there a way that we could automate away all this complexity? We realized that we could leverage the declarative nature of GraphQL. The fact that the capabilities are expressed in this declarative way, saying what they can do, not how. And we can combine a bunch of smaller GraphQL APIs into a single large one for clients. We do this by introducing a schema registry, which is a part of the Apollo platform. And then all the teams owning microservices can contribute smaller bits of GraphQL schema to the schema registry. And then in turn, it automatically updates the gateway, making that piece in the middle of your infrastructure much easier to operate and maintain. This allows the teams that own the microservices to continue to operate independently and autonomously, and allows us to split up our graph by separation of concerns. The schema that I showed earlier that had both products and reviews maybe should actually be split up into two different schemas owned by different teams. The products team would have data stores with all the product data and would provide a GraphQL schema that expresses the capabilities that they can provide. And the reviews team would have different services and different data stores and provide a GraphQL schema that expresses all the capabilities they can provide. And there can be overlap between the two, like creating this relationship between the product and the review in the review subgraph. When we take these two subgraphs and we combine them together, we get what we call a supergraph. The supergraph is the heart of the federated GraphQL API and makes GraphQL APIs easier to build at scale. There are two aspects I want to cover very briefly and how the supergraph works. The first one is composition. This is the process by which we take multiple smaller GraphQL APIs and compose them into a single supergraph API that includes all the capabilities from the smaller ones, as well as enough metadata or routing machinery so that that automated gateway in the middle of your infrastructure can appropriately fetch those capabilities from different microservices automatically. The other part to the supergraph is query planning. Once we have a supergraph schema, we can take any operation that declares all the requirements for a client and then run it through a query planner to generate the discrete set of steps needed to fulfill that operation. A query plan is really similar to the explain functionality in SQL. It shows you exactly what the engine is going to do in order to fetch all the data. We have some great docs on exactly how this works, but the heart of it is that it's sequencing a bunch of fetch calls to different microservices, either in sequence or in parallel, or sometimes in batch, which is how we solve the infamous n+1 query problem in GraphQL. So we worked with hundreds or thousands of companies building out federated GraphQL APIs, doing some amazing things. And we've learned a lot over the last few years. When we started looking at what we could do to improve federation, we realized that there was enough in there to build a whole new version, which we called Federation 2. We took a lot of lessons from our customers and converted them into improvements. And I'd like to cover a few of those today. We grouped the lessons in a few different categories. The first one being a developer experience, then collaboration, ownership, and finally migration. So let's jump into this first lesson. Number one is that small developer experience improvements really go a long way to making federation easier to use and easier to adopt, especially at large companies where you're going to have to teach this to everyone coming into your API. We started by simplifying the syntax. Federation 1 required a lot of keywords to express the relationships between the capabilities in one subgraph and the capabilities in another. We realized that a lot of these keywords were actually pretty unnecessary. And so when writing Federation 2, we took the opportunity to remove a lot of those keywords and make the schemas that you write when contributing to a federated graph much more like a normal GraphQL schema. We've added new keywords, but as you can see on the right here, even with the new ones, the whole thing is a lot easier to read. And it's a lot easier for someone new to Federation to come in and start contributing from day one. With these new keywords, we wanted to make it really easy to understand where they're coming from and what they do. So we added this syntax where you can link a specification to your schema and import exactly the keywords that you need for this particular subgraph. So if you're reading a subgraph and you see the key directive and you want to know what it does, you can find the link and then click on the URL to get to the spec and read exactly the definition of that directive. We also allow for renaming directives in case you have a conflict with your existing schema. This is really great because it's a lot less boilerplate while being a lot clearer in the definition of all these directives. In Federation 1, when two subgraphs are not compatible, it results in a composition error, and it could be at times difficult to determine what the source of that error was, especially if you have a graph of 10,000 types and dozens of subgraphs. So we took Federation 2 as an opportunity to rewrite all the diagnostics that come with composition so that the errors are significantly clearer. It's a lot easier to debug. We also added a new kind of diagnostic called a hint, because sometimes subgraphs diverge in compatible ways, and you want to know about that because maybe you typoed it and you want to fix that quickly, or maybe you're in the middle of a migration and these things diverge on purpose and you want to know when that migration is over. So these make it a lot clearer to debug and make the whole process of building a federated graph much easier. The second category of lessons is around collaboration. And the biggest lesson is that we realize we definitely don't want to block development when teams are having to coordinate schema changes across multiple subgraphs. Here's an example. So say we have a customers team that owns customer data, and all customers have a name. We also have an employees team that owns employee data, and those employees also have names. A cool aspect of federation is that while these two graphs separated by concern can define their own types, they also will often choose to share types, creating consistency across your whole API, making it a lot easier for clients to use. But this consistency brought some overhead. If a team wanted to introduce a change to a value type, a shared type like this name field, that change actually breaks composition and you're not able to move forward until all the subgraphs agree upon this change. This is really important for making the APIs really predictable, because if we didn't have that restriction, we allowed this change to be made, and someone then tried to fetch the customer's nickname, which doesn't exist in their subgraph, that would be a hard failure and lead to some unpredictable side effects. So we started with a strict model and then realized that it actually caused a lot of friction for developers. Waiting for all teams to agree upon this type was often too slow of a process, especially if one of those teams is on a different side of the world and is just going to sleep when your team is waking up. We built a whole system called Managed Federation that makes sure these issues don't actually affect things at runtime, but we realized we did want to make it a lot easier at development time. So we changed the model to make things a little bit more relaxed. Often, we can figure out how to merge types that are divergent automatically, and there's nothing more you have to do. But in the cases where there could be hard failures and unpredictable side effects, we added tools like the inaccessible directive that allows you to hide a piece of schema until everyone agrees. This allows all teams to move forward and continue to make unrelated changes while things are in disagreement. And once everything all the teams are on the same page, then we can remove this inaccessible directive and make it available to customers. Similarly, it's common for teams to need to move capabilities from one service to the other. This is really common when you're moving from maybe a old monolithic graph to a set of microservices. But the ability to provide the same capability to two services was something that Federation 1 just didn't allow. The query planner wouldn't know which one to choose. So if you tried to do this, you would block development for other teams while you went through the complicated coordination process of adding the field here and removing it there, which we call the schema shuffle. It's so common. In Federation 2, we added a new directive called override that allows both of these subgraphs to provide the same capability, but give a hint to the query planner about which subgraph to prefer. This allows teams to perform the schema shuffle at a much more leisurely pace and also not block other teams from making API changes. The third lesson is around ownership and sharing capabilities. We realized that teams really cared about determining the source of truth and making their API really predictable, but that sharing capabilities was really important both for migration purposes and for optimization purposes. In Federation 1, the ability to share fields was both a little too strict and a little too permissive at the same time. Here's an example with this products and reviews subgraph example. There's a product team that provides product details, like the product name, and the reviews subgraph can also provide product data. They may choose to denormalize that data into their own databases just for efficiency purposes. By providing the name using the provides directive, it means the query planner can skip a whole request back to another subgraph and make the whole request faster. But this did require a lot of boilerplate, and it actually didn't work with complex data structures, something beyond a simple string. So it was too strict in that way, but it was also too permissive in the fact that the product team couldn't keep other teams from doing this. If they wanted to be the single source of truth for a product's name, perhaps because it changes too quickly and they don't want the data to get out of sync, there was no way for them to assert that other teams shouldn't be able to provide this. So we made the whole model more flexible and removed a lot of the boilerplate, but we also made it opt-in. By using the shareable keyword, The products team can say, I'm only going to allow other teams to provide this field if they have a copy of it. And then the reviews team just has to say, I can provide this field and I know it's shareable. And they don't have to go through the whole boilerplate of adding the provides directive. The inspiration for this model came directly from our customers, and I think we ended up in a great place through that collaboration. Finally, I want to talk about migrations. Most of our customers are going through some kind of migration while they're working with us, either moving from REST APIs to GraphQL, monoliths to microservices, or something unrelated like moving to Kubernetes. So we didn't want to add a lot more tasks to their roadmap just to have them take advantage of the improvements in Federation 2. We did this in two ways. For starters, we made Federation 2 a very incremental upgrade. You can upgrade one subgraph at a time, and each team can do it at their own pace. We do this by having an upgrade algorithm within the composer that converts Federation 1 subgraphs into Federation 2 subgraphs before composition. What's great about this is that means you get all of those improved diagnostics, better error messages, and hints because the composer really only sees Federation 2 subgraphs. The other part of this is around query plans. We talked earlier about query plans being the discrete steps that needed to resolve a complex operation distributed across multiple microservices. And we can build these query plans in advance. We built a tool that allows you to do this just on your laptop. You can take the last month's worth of traffic, which we store in Apollo Studio, and run them through both versions of the query planner to see the resulting query plans. You can then run a diff across those query plans to see if the steps to resolve an operation change. If they change, then you would actually have different behavior at runtime. If they don't change, you know that Federation 2 is a great drop-in replacement for what you have in Federation 1, especially because you're going to get all the improved ergonomics and diagnostics of Federation 2. So having all this confidence by comparing query plans and using the declarative nature and statically analyzable nature of GraphQL is a really powerful aspect of the design of Federation. Before I go, I want to touch a little bit on the future of Federation. Federation 2 is the foundation upon which we plan to build some amazing new features and capabilities, making it much easier to build GraphQL APIs at scale. We have a roadmap that we published to GitHub, but some of the things that bubbled up that I want to touch on are the ability to compose user-defined directives. This will allow teams to add additional metadata to their subgraphs and have them end up in the supergraph. This will be great for documentation purposes, letting clients know what they can do with different parts of the graph, but also it will provide a foundation for building new features like caching, rate limiting, and authorization that it can all be run inside that automated gateway in the middle of your infrastructure. We're also really excited to teach the query planner about the defer directive, as well as real-time features like subscriptions and live queries. And there's a lot more, so please check out our roadmap. So thanks so much for coming to this talk. I hope you learned a little bit about Federation, why we built it, and all the great improvements, ton of hard work that went into Federation 2. Here are links to all the resources that were in the talk, and I hope you have a great day.
With that, DZone would like to thank Lenny for a great presentation. DZone would also like to thank Apollo for providing the audience with a great webinar. Lastly, thank you to everyone who attended today. We hope you learned something new that will help you in your developer career.